we've talked about polynomials before, but let me refresh your memory. A polynomial is a function that looks like this. It's some linear combination of powers of x. These a's in front of the powers of x, these are all real numbers. For example, 5x cubed plus 6x squared plus x plus 1 is a polynomial. These a's in front of the powers of x are called the coefficients of the polynomial. The highest power of x appearing in the expression is called the degree of the polynomial. There's a typo there, that should be an x. Well, here's a polynomial, p of x. It's 3x to the 5 minus the square root of 2x plus pi. You see that some of these a's are 0 in this because the power x to the 4 doesn't appear here, so its coefficient is 0. And the degree here is the highest power appearing in the polynomial, so that's 5. And the coefficients are a0 is pi, a1 is the coefficient of x to the 1, which is minus the square root of 2. a2, a3, and a4 are 0 because you have a phantom 0 times x to the 4 plus 0 times x to the 3 plus 0 times x to the 2 in here. a5, the coefficient of the highest power, is 3. If the degree of the polynomial is 1, then the function is called a linear function, and the graph, as we saw before, is a straight line. If the highest power is 2, then it's called a quadratic, and this is something we've looked at in detail before, and the graphs are parabolas, and you know how to graph those by completing the square. And if the highest power is 3, then it's called a cubic. The graph has at most 2 bumps in it, and we'll see why that's true later when we study derivatives. Now, one interesting little thing about polynomials and the graphs of polynomials is the following. Remember we said that if I have 2 points on a line and I join those 2 points, then I get the rest of the line. So they completely determine the linear function that fits those 2 data points. Likewise, if I have 3 points on the graph of a parabola, then there's only one parabola that actually goes through those 3 points. So the quadratic polynomial that goes with the graph is completely determined by those 3 points. 4 points determine the graph of a cubic. So if I have 4 data points on a cubic, then I know the equation of the cubic. And if I have n plus 1 data points on the graph of a polynomial of degree n, then the formula for the polynomial is completely determined by those n plus 1 points. Now that's hard to prove. It belongs in higher algebra, but nevertheless it's something we can use. We can get a feel for what's going on from an example here. Suppose we're looking for a cubic polynomial which fits these 4 data points. So we're looking for a function of that form which fits this set of data. Now remember when we talked about polynomials before, we said that if p evaluated at some a is 0, then x minus a divides p of x, or is a factor of p of x. So we have 3 values here which give us 0 in the polynomial. So this tells us that x minus 1, and x minus 2 are factors of px. So that means px is something times the product of these 3. Now px is a polynomial of degree 3, and when I multiply these 3 out, they give me another polynomial of degree 3. So the product of these three is already a polynomial of degree 3. And if I were to multiply by any other polynomial with an x in it, I would get a degree 4 or higher polynomial. So that tells me that this factor is a polynomial of degree 0, or just a constant. So now I know that the equation of my polynomial is c times x minus 1 times x minus 2 for some number c. How do I find that c? Well, there's one piece of data that we haven't used here, and that is p of minus 1 is equal to minus 6. So we now know two things. We know that p of minus 1 is minus 6, and p of x looks like a constant times x minus 1 times x minus 2. So let's put these two pieces of data together. We plug in x equals minus 1, and we know the left-hand side of this second equation must then be minus 6. And that tells us that minus 6 equals minus 6c. And of course that tells us that c equals 1. So now we know our polynomial completely. The c is 1. P of x is then x times x minus 1 times x minus 2. If you use your distributive law to expand that, you get it's x cubed minus 3x squared plus 2x. Now the graph of this polynomial, which we'll be able to do quite easily after we have studied derivatives, you could plug in a few points here. You have p of 0 is 0, p of 1 is 0, p of 2 is 0, and p of minus 1 is way down here. It's minus 6. This graph has two bumps, and again, after we've studied derivatives, we'll be able to get the graphs of cubics pretty easily.